Imagine holding a window screen out in a horizontal rainstorm. If you hold it vertically, the maximum amount of rain passes through. But if you rotate it flat, the rain just skims across the top and nothing goes through. Look at this diagram to see how that maps directly onto physics. The red lines represent a uniform electric field, E, passing straight through that flat area, S. This count of field lines penetrating a given surface is what we call electric flux. When tilting a surface, a geometry changes. We measure the angle against the normal vector, that pink line pointing perpendicularly out of the plane. Notice angle theta is defined between the green electric field and the pink outward vector. Because the calculation depends on this alignment, the flux formula is E times S times the cosine of theta. And as this note confirms, the result is a simple scalar quantity, measured in Newton meters squared per coulomb. The flux depends on more than the strength of the field or the size of the area. It measures the alignment between the two. That works for flat planes. But on this curved surface M, every area ds has a normal vector pointing in a different direction. To find total flux, you'd calculate a surface integral, adding every infinitesimal dot product across the shape. For closed 3D shapes, area vectors always point outward. When pink field lines point out in the same direction as S1, the flux is positive. When field lines enter the shape against the outward vector S2, the flux is negative. Think of the field lines like a flashlight pointing at your 3D shape. The shape blocks the light, casting a flat 2D shadow onto a wall behind it. In a uniform electric field, this projected area replaces the need for that complex integral. Since no field lines are created or destroyed inside the object, the complex 3D surface intercepts the exact same amount of field as its flat 2D shadow would. Let's test this logic. Here is a yellow hemisphere facing straight up into a uniform vertical electric field, red lines striking the curved dome. Projected straight down along the field lines, its shadow is simply its flat circular base, with area pi r squared. Now check this vertical cylinder in a horizontal field. Projecting its curved front half forward creates a flat rectangle, with width 2r and height h. To find the flux, we multiply the field, E, by this rectangular area, giving E times h times 2r. Consider this diagram of a yellow cone in a horizontal field. Pause the video and try to determine the exact shape and dimensions of its 2D shadow. Solving for 3D flux in uniform fields is a test of spatial reasoning, translating a solid object into a basic 2D shape. Projecting horizontal field lines through that cone creates a flat triangular shadow. Its base spans the diameter, 2r, and height is h. The shadow's area simplifies to r times h. Multiplying this area by the uniform field gives the total flux, ERH. For uniform fields, the 3D shape and its 2D projection are linked. A hemisphere becomes a circle, a cylinder becomes a rectangle, and a cone becomes a triangle. While surface integrals are necessary for complex real-world fields, you can avoid them here. When tackling textbook uniform fields, look for the shadow.